So we have Professor Joseph Pelton, Joe Pelton, which is Dean Emeritus at ISU, and he's the co-author and editor of the Small Sat Handbook, edited by Springer. We also have Professor Jordi Puig-Suari, Emeritus Professor at Cal Poly, and Taiva co-founder, so an authority in the world of CubeSats. More than 20 years ago, he was one of the pioneers on the field. We also do have Professor Scott Madry, founder and president of Informatics International. He also is a research associate professor at University of North Carolina, Chapel Hill, Research Laboratories of Archaeology. We also do have Professor Peter Martinez, which is the executive director of the Secure World Foundation. And we also have Kirutika Devaraj, that is today at Planet Labs, director of software engineering on aircraft avionics. And she was in the past at NASA working on radiometers and other instrumentation for missions like Jupiter and others. So very distinguished speakers, the floor is yours. Thank you so much.
Joe, you're muted.
I think somehow we got muted.
Please unmute the...
I think we have a really great panel today. We have a lot of things in common in that Scott, Peter, and I, and Dr. Deborah, I'm not quite sure how to say her name quite well, but I've worked with her very closely in that we all work together on the Handbook of Small Satellites. And of course, we have Jordi, who is the father of the CubeSat. So we'll try to keep this moving along. I know it's late in the evening there, and so we'll try to be entertaining and informative. And we're going to start out with the father of the CubeSat, who has contributed a great deal to the start of a whole new small sat industry. And I'm intrigued by the fact that we now have what's called Pocket Cube, which is 1/8 the size of the CubeSat. So anyway, I think we'll skip the two slides I was going to use,
yes,
and just go right to Jordi.
Yeah, perfect. Thank you so much. And it's a pleasure to be here. I'm really happy that I have this opportunity to talk to you guys and be in this great panel with a bunch of people I know that are great as well. And I don't have any slides. I just want to make a few remarks and kind of put things in perspective from my personal opinion. And the first question is, what is small? And is small what's important? There's a lot of effort going into this new space and agile space. There's all these names that we try to give these things because size is not really the key parameter. You know, you can send a very small mission to Pluto with RTGs and cost billions of dollars, and it's really traditional space, regardless of the size. So I think what the small sat community has accomplished lately is we've finally succeeded in making it faster, better, cheaper. That goal that NASA tried years ago and failed. And I think the big reason it succeeded is that we're faster, better, cheaper, but we take more risk. And in the past, the risk was not acceptable. And that is the big changer, in my opinion, is the risk posture and the ability to say, well, I'm willing to take more risk because it allows me to use commercial off-the-shelf components with higher performance, make cheaper satellites, make them smaller, and maybe they don't have the lifetime that the other ones have. And that's really, in my opinion, been the big thing that has changed. It's really interesting because that's exactly the key to how CubeSat started. And it's something that we did not understand at the time. But Bob Twiggs at Stanford and myself, when we started, we were looking for an educational component. So the idea was to train students. So what we didn't realize at the time is that by being an educational system, we had no mission risk. If the spacecraft failed or the mission didn't provide the data that you wanted, you had already trained the students, which was the big goal. So we could fail and succeed, which was an unusual position to be in compared to normal satellite systems. And that allowed us to try things and demonstrate that these commercial off-the-shelf components at these very small spacecraft could actually work. And then industry and other government agencies, you know, Planet was the first one out there, decided, okay, these systems work. I can make something useful and provide a mission. But we had taken a lot of the risk out of the picture with the universities, but our objective was not the mission. So that allowed us to take a very, very large amount of risk that in those days, the industry was not allowed to do. And that, I think, it's something that we need to not forget. And that is where, if you look at pocket cubes, you know, they're even smaller, they're trying smaller things. They're emerging in that same no risk mode where they're used by students or amateur organizations, and they can try things and test it. And if it works, then we can implement it in commercial or government systems. The other thing that was key to that is the ability to actually launch. And that's where the standard, the CubeSat standard and deployers and all that played a role, is in making the launches available. Because before that, you could go do a risky mission, but you couldn't fly. And that was a problem. So I think that we have covered. We have figured out how to do it. I think it's still important for the NASAs of the world, the ESAs of the world, the JAXAs of the world, even the companies, although I think the companies are smarter about this, to be in a mode where risk is more acceptable. To say, we're doing things that we haven't done before, learning is part of the mission. And maybe the data didn't come down because we had a failure on a system, but we learned something. And that's valuable information. It's hard to do when your missions are Mars rovers that cost $1 billion. But if it's a smaller system, you are allowed to have those learning experiences, which I think are very important. So that's something where I commend the constellation developers like Planet, because they have this, each individual satellite is not the system, so they're willing to take more risk and they try things. And I think we need to encourage everybody to not forget the early days of space where, you know, we would launch rockets twice a week and they all blow up, and we kept trying. We never said, oh, the rocket exploded, we need to spend 3 years figuring out what went wrong. And we're willing to take that little bit of risk. So that's the one thing that I wanted to put in there, that I think small is a byproduct of this ability to use different components and different systems. But maybe when people say small, they mean something else, and we need to make it clear. And then the last thing I wanted to say is, looking at the future, is what is there that small sats won't do? Because we're getting to a point where the resolution on observation satellites that are small is getting really, really good. I mean, I don't know if we need to get any better. We have radar satellites that are small. We have now, they're putting small geos in orbit for communications. So I don't know if this idea of small satellites has been a small part of the industry is going to remain correct for a long time. I think that it may be that a smaller size of satellite is going to become the prevalent system out there. And the ones that will be unusual will be the big multi-ton spacecraft that we were used to as the primary industry satellites. But we'll see what happens. But I think part of that is already happening. And that's it. I really want to make sure we have time to talk.
Okay, thank you very much. I think, Scott, I will show the two intro slides. I did want to hear Jordy's comments first to put them in context. So can you put the first one up? No, yeah, that one. Okay. So can we see the whole thing? Yeah, okay.
Yeah.
Just to explain the tremendous range of small satellites that we go up to the mini satellites that are 100 to 1,000 kilograms that are in a lot of the commercial systems that SpaceX and Blue Origin and Amazon are going to put up. Then we go down to the nanosats, which is basically where the CubeSats are, of 1 to 6 unit CubeSats. Then below them to pocket cubes, to pico satellites that are 100 grams to 1 kilograms, and even femto satellites that are also called chipsats that are 10 to 100 grams. So we can really go 5 orders of magnitude in different sizes, what we call small satellites. So the next slide. This is just to give you a feeling of how many of the constellation of small satellites are happening right now. And the biggest ones are, of course, the SpaceX Starlink that's going up, and then V-band. And all together, if all of those satellites are launched, there could be 10,000 satellites just in that one SpaceX constellation. So just to give the idea that we have a tremendous number of satellites that are being planned. There's a new Chinese system that's going to be quite large that I think Scott's going to talk about. So with that, just to give you an idea that this is a real explosion of small satellites that are happening now, and that the sizes are tremendously broad from the chipsats up to 1,000 kilogram satellites. So Scott, it's all yours.
Okay, so hi everybody, I'm Scott Madry. I have many fond memories of spending very hot summers around the world with ISU. And so my love goes out to all of you folks wherever you are. So I come from a remote sensing background. I started in the early 1980s. And so talking about changing paradigms, you know, this is what we now call remote sensing 1.0, epitomized by ESA's ENVISAT. That's it on the right in its stowed configuration. This is not a small sat. Only cost just under 3 billion euros, 8,000 kilos, launch 6.5 kilowatts of power. Massive thing once it's in space. It was actually designed to barely fit in the shroud and the mass launch capabilities of the Ariane 5. And this was the paradigm. Huge satellites took decades to design. And this was the existing remote sensing paradigm for many decades. And now, of course, all that has been turned on its ear. And you're going to hear from the source about Planet. So I'm not really going to talk about it too much, but other than to say that everything that Planet has done was completely wrong. It was completely against the existing paradigm. It was all wrong. They even put art on their satellites. I don't think ESA or NASA ever allowed anybody to draw on the satellites. It was all wrong by the existing paradigm, and yet it was absolutely brilliant. And we'll hear more about that in just a second. And so I, as a teacher and a user of remote sensing data, and Joe, I noticed I don't, well, never mind. Joe and I have had the opportunity to teach with Peter Martinez down in the Space Lab program at the University of Cape Town. Here's some Planet data that they were kind enough to provide me for the teaching. And you can see this beautiful, beautiful high detailed imagery of Cape Town. And this is now becoming remote sensing 2.0. But I want to go beyond that. I want to talk about what my vision is of where I think this could go and where it should go. And what I think we need to begin looking at is actually implementing the integrated system of systems that includes not only small sats, not only traditional large government designed and built operated satellites, in GEO, in LEO, airborne systems, UAVs, terrestrial, in situ networks. What we need to begin moving towards is the functional integration of these systems into what I think is where we need to go. And so those of you who attended some of my ISU lectures long ago may remember me talking about going from data to information to knowledge to change. And what we need to do is go from those massive numbers of bits and bytes that are going to be streaming down from space, the petabytes, process that down into useful information. And we become really great at designing and operating these systems and collecting this data, but we still really suck at convincing people based on the data what needs to be done. And so I think we have a lot of work to do going from knowledge to actually instituting change. And so the future, to my mind, I've coined this concept of disruptive geomatics. And my concept of this is the functional integration of all of the remote sensing capabilities, geographic information systems, of GNSS and PNT systems, in situ telemetries, and all of the big computer revolutions of big data, really big data, AI, the Internet of Things, decision support systems. We need to begin working on putting all this stuff together at all scales in near real time to provide global and low cost access to actionable information for the benefit of all humanity. And this is where I think we need to begin to think about. So my analogy is we've got all the pieces laid out on a table of all of these capabilities. And now what we need to do is make the next great leap, get the next group of space disruptors, and I hope there are some of you sitting there thinking about this right now, to take all of these pieces, put them together into a single system that actually works, that helps us address some of the many different pressing problems that our planet faces. And so that's the very short message I wanted to hand out to you guys, and make you think that we need to go from massive streams of zeros and ones from all of these sources into actually impacting decision making. That's a very hard stretch, and we have a lot of work to do. And so all you guys out there, get busy. And Joe and I and Peter have put together a bunch of books, the two handbooks. Peter and Renee and I did the book on innovative small sats. And last year I published a book on disruptive space technologies and innovations, where I talk specifically about a lot of these concepts. So that's what I wanted to talk about. And it's wonderful to get a chance to talk to all you guys. And I look forward to the questions and discussions.
Thank you, Scott. It really is interesting how quickly things are changing. I have a former student of mine who's working on a project that in theory will be able to give a complete multi-terabyte image of the Earth and close to real time. It's a very ambitious project, and it's amazing what may be possible with all of the new technologies involving things like automatic identification systems. There's a new system for geo imaging of RF geo imaging that gives a global picture of the Earth in terms of use of frequencies. So lots of change. So next we have the real deal of the information from a planet and what they are doing to change the world. So I will turn it over to Dr. Devaraj.
Thanks, Joe. So Planet was started 10 years ago now with an ambitious mission to image the whole world every day, making change visible, accessible, and actionable. And when we started, we didn't have a lot of, we didn't have a lot of ideas about how to go about doing this, except that the founders were very willing to take risk, as Jardi mentioned. And next slide.
Scott?
Yeah. From there to today, a decade later, what we have is an industry-leading Earth observation satellite constellation. We have over 133 CubeSats. We call Dove line of satellites. Those are the satellites that carry the ART, as you can see. And our mission with the Dove constellation was to image the whole planet on a daily basis. So they are launched into a sun-synchronous orbit, and they are nadir pointing. And anytime they are over land and it is daylight, they are imaging. And we collect a ton of data at about a 4-meter resolution on the ground. And if the data is downlinked to the ground today, and whenever they see, we see something interesting, we can go back and revisit with these 21 SkySats that we have up that can provide a roughly 65 centimeter GST. And so you can, in theory, create this map of the whole planet at the medium res, but wherever things are changing, wherever there is interest, you can sort of zoom in with SkySats, and that's what we have been building up. Next slide. The planet approach to Earth observation is different. I think the slide, text isn't showing up, but that's okay. But basically, instead of going for a $1 billion, super expensive, super complicated satellite that takes a very long time to build and launch, we reduce risk by distributing our satellites across n number of satellites. And so we are able to move fast, take substantial risk, because if any one particular satellite fails, you don't risk the mission success. You can be at a slightly reduced capacity. So disaggregated constellation allows us to take risk, and it also allows us to make frequent changes to our satellites. So our satellites, for instance, the CubeSats in particular, they have a 3-year operational lifetime. Why is it 3 years? All of you have your cell phones in your pockets, and the consumer electronics industry is moving so far ahead in with what they're doing, and they're driving innovation. You change your phones every 2-3 year time frame, and that's the goal with Planet's CubeSats. We want to be on top of the technology we are building, which means we need to be replenishing these satellites every 3 years, because the industry has changed. So we are able to, at a constant pace, replenish the satellite constellation with newer and newer sensors, and newer battery technologies, and newer communication systems. And we have we can put GPUs on board now that GPUs are becoming commonplace on the ground, for instance. When we when Planet pioneered the agile aerospace philosophy, it allowed us to build 15 iterations of these CubeSats in a mere 7-year time frame. And that means that we are continuously iterating the design, and the design life cycle is about 6 months. And the focus is on leveraging other industries' R&D. For instance, the batteries we use come from billions of dollars in investment that the automotive industry has put into the battery technology. So we are actually borrowing technology from the automotive industry for that. And some of, we also borrow some of the imaging systems we use from the medical devices industry, because billions of dollars have been sunk in that industry. And the same thing with the processors and the solid state devices that we use come from laptops and tablets. So in a sense, as a big space company where you're expected to spend billions of dollars into all these, the Planet we've done it is to borrow things from industries that have already sunk in billions of dollars into their R&D, and we do space qualify as needed. So we take these components, we would go through whatever appropriate qualifications needed to make sure they'd survive in LEO for 3-year mission. On the CubeSats, the SkySats, they have a 6 to 8 year mission lifetime. So the amount of qualification testing is different. We also built up a manufacturing facility in-house, and this was essentially to help keep up with the pace of change that needs to happen. If we are launching a fleet of, say, 20 satellites, then 20-30% of those satellites will have experimental configuration. So each of them, more or less, of the 30% would be unique, and they'd have, one of them might have a different battery, one of them might have a different microprocessor, one of them might have a new antenna, and we are able to test out these technologies. So we call them tech demos. We would launch tech demos. We would understand how these systems are performing on orbit, and 6 months later, those would roll into the nominal operational configuration. So having a lean manufacturing facility where we can, produce 10, 20, up to 40 satellites per week has been super helpful in cutting short the timeline from design through production. Next slide. And then we also launch frequently. We end up having at least 3 to 4 launches per year. We had over 400 satellites that have successfully deployed on 32 launches. Of course, we've had a few failures along the way, but launch is becoming less of a problem than it used to be even 5 years ago. There are a number of options available. Next slide. This is a video. I don't know if the animation is going to show. Scott, can you click? All right, doesn't look like it, but it was just gonna, this is a Earth observation satellite constellation in a sun-synchronous orbit, where it shows that as the satellites are going over land, they are collecting, a specific area, and we are constantly imaging. Next slide. I think if we can just skip to the next slide. All right, while the slides are loading, I can talk about the fact that, now that you have these large satellite constellation, you built up the manufacturing facility and you're launching all these satellites into orbit, you need a way to manage these satellites. And traditional way of managing would be to have an operator or multiple operators, operate a handful of satellites, and that doesn't scale when you have hundreds and sometimes like thousands that Starlink has. So we ended up creating our own mission control system that's fully it's autonomous. We also have a ground station network that's got about 50 different ground stations distributed in 15 geographically diverse sites. And we are able to monitor the health and status of the satellites on a very regular basis. We also get telemetry information from the satellite that and there are automated machine learning algorithms that churn through the telemetry and picks up any anomalies it sees in the data, and then informs the operators and the designers if something is going wrong. And when we've done all this, we end up producing something like 25-30 terabytes of data per day. What that means is, as Scott said, now that you have these terabytes of data coming down, how do you get it to people? How do they ingest the data, and how do they extract the insights from the data? And that is the problem that we are currently working on. We have several different products that we offer to customers, and one of the products is a machine learning model that can identify and pick up objects. For instance, we can create a map of the entire road network on the ground, and if there's any change, we can automatically understand how the road network is changing in specific locations. So we are starting to create these the analytics products on top of the massive amount of data, terabytes of data that we are getting down. So that's what we are focusing on today. I'll stop here.
I think we have a problem with the slides, so maybe you could just.
I'm done. Yeah, I'm. Yeah, that's what I wanted to talk about, and that's that's what Planet is doing, and I'm very excited for what is to come in the decade, the decade of 2020. One of the like the era of 2010s, was filled with the access to space with frequent launches, using consumer and commercial off-the-shelf technology, taking risks and launching satellites. And the era of 2020 is still to be defined, but there's a ton of investment going in AI and machine learning, and it will be an interesting decade for sure.
Okay, well, thank you very much. Before we go to the last speaker, it does seem that Scott is telling us that, our last presentation explained that it's small satellites are enabling much more sophisticated data analytics and useful applications that we never had dreamed of before. And in the communications world, these large networks are basically not so much telecommunications networks as very advanced networking technology, and being designed to try to accommodate the latency requirements for 5G and even 6G applications, including things like driverless cars and other applications related to Internet of Things, which may become the predominant stream of data across the world, because there will be literally billions and maybe even trillions of Internet of Thing equipped devices. So it is a rapidly changing future, and small satellites in both the remote sensing and the networking world are making big changes. But all of these things so far have been on the positive side of what small satellites are capable of and what they might do in terms of new applications. But we come now to Peter Martinez, who's going to talk about, well, what are the regulatory and the legal and jurisdictional issues that small satellites, and particularly very large constellations of satellites, pose to the world community and the long-term sustainability of space. So Peter, it's all yours to wrap up.
Thank you, Joe. Thanks very much for the invitation to participate on this panel today. It's great to be back among dear friends and colleagues, and especially among the ISU community, even if it's only virtually. So great to be participating in this panel. And thank you for inviting me to talk about the regulatory issues. I think that we are all aware of the immense potential and promise that small sats hold out. And we just have to be mindful of the questions that they raise in terms of the sustainability of space activities, and also the fact that more and more actors are entering the space domain, which is a strategic and sensitive domain. And it's not really the small sats themselves that raise the questions. It's more the actions of space actors that we need to talk about. So I'm all for small sats. I think the technology is great, and it's amazing to see how it has matured over the last decade. So earlier on, Joe, you spoke about the huge range of sizes of what are collectively referred to as small satellites. And so from a legal perspective, there is no distinction between large satellites and small satellites. All of them are referred to as space objects under the international treaties and pretty much all of the national legislations that I'm aware of. In my career, I've had the privilege of having served as both a national regulator of space activities, but also done a fair amount of work in the UN Committee on the Peaceful Uses of Outer Space that looks at this from a sort of international perspective. And so that's given me some insights on the challenges of governing space activities, particularly with regard to small satellites. Small satellites do pose a number of challenges due to their small size, of course, which makes some of them, especially the smallest ones, very difficult to track. And we have had already regulatory challenges with the launch of some very, very small satellites that have been difficult to track and that have resulted in punitive actions from a national regulator. We also are seeing a very rapid proliferation, not only in the number, but also the diversity of space actors, and also all kinds of new kinds of space activities. And that is, of course, because small satellites, as we heard, allow groups with a higher risk tolerance to try all sorts of exciting new things in space. And so they are used as test beds for new ideas, for things involving, for example, close proximity operations, and other things that are, I think, foundational for a future vibrant space economy, but they also raise concerns in terms of safety and security issues because of the dual use nature of all space activities, or space technologies rather. And then, of course, because there are all these new actors, many of the actors coming into the space domain are, if you like, non-traditional. They are bringing in innovative new ways of doing things, but also they may not have the awareness that they're entering a sensitive and strategic domain. And so we need to work hard to raise this awareness. And I'm speaking here about certain approaches, such as, for example, the investment community, the venture capital community is playing a large and increasing role in space technology. And there's a certain mindset of, develop things quickly, fail quickly, learn from your mistakes, and so on. And while this approach is very fruitful in terrestrial applications, it can cause problems if systems are deployed to space before they are mature enough to be operated responsibly, and then for there to be a good control over these systems, so that we don't get stuck with half-deployed systems in orbit because the business initiatives that set up these systems may go bankrupt, and then there's nobody controlling them. So it may be instructive for this audience to describe the evolution of the thinking of the regulation of small satellites and space sustainability in multilateral fora like the UN. The UN began its space sustainability discussions in the mid-2000s with some work that was initially done by Carl Deutsch, and then subsequently picked up and really quite heavily promoted by Gerard Brachet, who was the chairman of UN Corpus in the mid-2000s. But really, the committee the UN only decided to formalize this in the late 2000s. So it was only in 2009 that a working group was set up to look at this in a systematic fashion. And this was very much due to the enormous efforts of Gerard Brachet and the French delegation at UN Corpus to raise the awareness of the international community to these issues. Now, there were a number of hurdles that had to be overcome in socializing this concept, particularly because when the conversation about space sustainability began, it was led by the largest space actors, the largest space nations. And so there were two issues as far as the emerging space countries were concerned. One was that some countries saw the concerns around space debris and the increasing congestion of space to be a problem of the major space nations and not really their problem. And it took some time for them to realize that all countries nowadays are critically reliant on space technology. And so therefore it's in everybody's interest that the space systems that we rely upon, that we take measures to ensure the continuity of space data that all nations rely on. There was another group of nations that was somewhat suspicious of the whole discussion of space sustainability, because it was felt that, remember, this was at the time when the small sat revolution was really picking up in a big way, and the technological and financial barriers to space were being drastically reduced, and so many more countries could suddenly participate. And then all of a sudden in the international forum, there's this discussion about concerns of space sustainability. And so a number of countries, quite justifiably, saw this as perhaps a pretext, as an attempt by the most advanced space nations to preserve their leadership on the pretext of concerns about the space environment. And it took a while to overcome these issues. But eventually, the working group got going, and it was a very international effort. In fact, the participation increased dramatically during the lifetime of this work at the UN. And towards the end, we had extremely good participation from close on 90 member states in these discussions. There were a number of guidelines that were adopted. I don't have the time to go into them in detail here, but just to say that these international guidelines address the policy and regulatory frameworks for space activities and are really very relevant to the small satellite community. And I'm happy to go into the details of these guidelines, but I think we should allow some time for questions. But just to say that if you have not seen the UN Space Sustainability Guidelines, that I would encourage you to take a look at them, because although the UN is well placed to recommend the establishment of, or well placed to recommend established international best practices for regulatory aspects with things such as licensing, trackability, registration, control, or the transparency of space operations, it cannot deal with other equally important aspects, such as sensitizing the new entrants to the space arena, including investors, about the importance of conducting space activities in a responsible manner. And this is a conversation that involves academia, industry, and the investment community and civil society organizations. So I'm really glad that this is on the agenda of this ISU conference. And just to conclude by saying that at the end of the day, just as on Earth, where each of us has to make conscious choices about how our individual actions affect the Earth's environment, so too in space, it is ultimately the individual space actors who will have to make conscious choices about how we conduct our activities in space in a manner that preserves the space environment for others and for future generations. So I'll stop there, and happy to, looking forward to the discussion to follow.
Thank you very much, Peter. We're actually somewhat modest to not note that you were the chair of the working group that used enormous tact and leverage and every other diplomatic skill you have to get unanimous agreement on 21 of these guidelines, and that you have had the good sense to turn this over to the new what it's called, I guess, the 2.0 initiative, to try to develop even better and further guidelines in this area. But you yourself made an enormous contribution to this effort. We do have, I think, some time for questions. Have we gotten any questions in on the chat line or elsewhere? If not, I would just pose to Scott that about the future of that. Do you see if you will, a combination of these applications into a more integrated type of capabilities for, if you will, detecting problems with, let's say, global pollution, climate change, or other issues that the world community faces? That, in other words, today there's kind of the networking and communications field, and then there's the so-called, I guess, geomatic field and so on. do you think that these space technologies could become more integrated and, like creating a kind of a global instant understanding of what's happening on Earth minute to minute and where problems are emerging and whether we can use this technology in a more integrated way?
Well, as I hinted at briefly in my part of the presentation, I really think we have gone as far as we can go under the existing paradigm. We've made excellent efforts in the United Nations, GEOS. There have been many excellent attempts, much hard work, good work in trying to create system of systems, getting governments and remote data integrators working together. But I really think we've exhausted that approach, which is why I've tried to coin this idea of disruptive geomatics. We need some smart ISU students to come in and kick over the existing paradigm of how we do this, how we go from photons to electrons to neurons to what I call actions, making good decisions. And I think, honestly, my feeling is we have exhausted the existing paradigm, and we need to have some really young, smart people come along, like Will and the others at Planet came along, like Elon came along, and come up with an entirely new approach, an entirely new way. And I don't know what that is, because I guess I'm too rooted in the old existing paradigm. But my concern is I think we've exhausted the options that we have under the existing paradigm, and we need some young, really smart new folks to come along and come up with a completely new way to approach this. Or, as we've all seen in the weather lately, we're all going to be in big trouble.
Well, I just finished my, I guess it's 55th book called Space and Sustainability, that does look at 12 existential threats to humanity, everything from asteroids and coronal mass ejections from the sun to pollution and climate change, and how we can use space to address these challenges. And frankly, I fear we're not doing nearly enough to use that technology in a synergistic way to address the challenges. And so I, like you, hope that some of the bright young ISU grads or students can come up with some new solutions.
I would be very curious what our other panelists
Right.
think about that question too.
Right. Jordy, do you have thoughts?
Well, I think that you guys have said that the gist of the question is that we need new ideas, and the big problem is that we get rooted in a way of doing things, and that's really what needed to happen with space, where everything, you couldn't fly anything that hadn't flown before, which meant you could never use new technology. That put space behind 10, 15 years. Failure is not an option. That was really bad because it meant that you could never do anything new. And I think that sometimes regulation and mil specs and all these guidelines on how to do things means that you cannot do it in any other way. And that's a problem. So there needs to be a willingness when that young ISU graduate comes with a new idea. There needs to be a mechanism or a forum or a system for that idea to be tried. And the one fear that I have is that you overregulate the system and overspecify the system so that new ideas don't fit in the current paradigm are impossible to try because you're violating some specification or some regulation that doesn't allow you to try it. Clearly, we do need regulations, but I think that we need the flexibility for new ideas to be tried somehow.
Dr. Devaraj?
Yeah, I have a similar take on this, but I have one point which is slightly different but related. So when companies start, they they have some investor funding to try to build and de-risk technology, but very soon you need to go from there to how do I commercialize it? What is the commercial application and use case out there that can justify the company even existing? And communications, we can justify that. And Earth observation, Planet was one of the first companies that had to figure out how to justify Earth observation business to outside of DNI customers, because our DNI customers are less than 30% of our users. And it is good in a way because we can, we don't become get consumed as a subcontractor in the end, which is a very good thing. But then when we talk about all these ambitious goals to prevent and mitigate climate change effects and pollution, there also needs to be users on the other end, that is not just NOAA or NASA or the ESA, that can use the data and make the companies if not profitable, at least make it a commercially viable business model. So with the I think the environment is changing. I think ESG, environment and sustainability goals are becoming more and more critical for every organization out there, and companies are trying to buy carbon offset points, and I think as corporations and organizations realize that they need to pull their weight to mitigate the effects of climate change, then operators like Planet and other people that come along that are working on sustainability goals will be able to justify their business model. But I think there needs to be a push-pull for this to happen.
Well,
Joe, we do have, I found some questions that came in.
Okay.
And we have
Peter quickly comment on that last question, or let's go to the questions, I guess.
This one actually would be for Peter too, from one of the audience. Why do regulations seem so far behind for the new mega constellations? And there we go. And how could this be accelerated so that we don't actually get to the point where we have problems like Kessler syndrome?
You're on mute, Peter.
Sorry. Thanks, Scott. That's an excellent question, and it's something that we have grappled with both at the level of national regulators and at the international level. That the pace of technological development has outrun the pace of the regulatory developments. And one of the you will, for example, not see any reference to mega constellations in the UN guidelines, or even things like the removal of debris objects, although those were points that were discussed somewhat. This is a big challenge, and I think that we have to, just as you mentioned, there's this kind of paradigm of Earth observation. I think we need to revisit the whole paradigm of space regulation and how that is done, and figure out ways of involving the private sector and academia in these regulatory discussions to kind of fast track some of them. We also need to, regulators all agree that it's important to come up with regulations that are future-proof in a way, in the sense that don't get overtaken by developments. And most regulators that I've spoken to are very sensitive and aware of the point that Jordi mentioned about not having regulations that stifle development, having regulations that allow flexibility. So I think there is this general awareness of not over-regulating. But it's a challenge, and particularly with regards to how we are going to avoid fragmented governance of space activities, which could lead to regulation shopping and potentially conflict further down the road.
Do we have a final question? Because we're close to the end, Scott.
Here we have questions on standards. So how do we see CubeSat, smallsat standards moving forward in the future?
I think that's a Geordie question.
That's an interesting question, and it's something that it actually goes back to the idea of stifling innovation. You know, if you make the standards too rigid, then people cannot do anything. And that's another one of those things that CubeSats were really good at that we didn't know we were doing, is that the standard says nothing about what you put inside the spacecraft. So the thing that standards in the CubeSat case were excellent for was providing access to space, making the launch simpler, because the launch vehicles can provide accommodations for a generic CubeSat and anybody can use them. And the CubeSats can fly on any vehicle. And I think that there's still a reason to do that. It gets more difficult as the spacecraft get bigger, but ESPA is starting to become a recognized standard. And the other thing that it goes back to this idea of the old way of doing things. There is this tendency for satellite designers to try to optimize their design. You know, and my satellite will weigh 10 less kilos if I make it a circle instead of a square. But that violates standards and makes it harder to launch. So we need to get people in a mode where maybe it's not the most streamlined, perfect spacecraft, but it's easier to launch. And I think that's where standards come along. And we've seen that. I mean, the shipping industry with containers is the best example. You know, the container is this size, and you just make it fit in. And sometimes you modify your product so that it's portable in a container because it makes it so much easier to transport. And I think that's where we should be looking at, is what makes the transportation layer, from Earth orbit to wherever you're going. It may be LEO, it may be GEO, it may be Mars, the easiest. And standards do that. Standards make that easier. So I think there's still a place. It's just difficult to convince the space designers sometimes to not make the perfect spacecraft for their mission.
Geordie, I congratulate us and all the speakers on an interesting presentation. I know the audience out there would like to hear 3 more webinars before they have a chance to break and get together and network, but I think we should let them go. I do think that standards is a really complicated issue. In our lab back at my university, we had a bumper sticker that said, "We love standards. That's why we have so many of them."
Yeah.
So, but anyway, sorry that we could not be with you there for the alumni weekend. But we have many fond memories. Scott and I were at MIT when we founded this organization. There we have it. So 1987, ISU has come a long way, and I send my best wishes to all, particularly to Juan de Daume, who has been an excellent president of ISU, and we're looking to the next period of progress for the ISU. So good night, and thanks for being with us for this presentation, and thanks to all of our fine presenters.
Bye-bye, everybody.
Bye.
Bye.
Bye, everybody.
Thank you. Goodbye.